All right. So we're going to end up with a more cheerful note. I'm kidding. That's not going to happen in this presentation. But what is going to happen that we want to talk about joining different disciplines into a very important question that has been implicitly alluded in many of the talks, that has to do with the impact of climate change on future migration. And it's kind of interesting that the disciplines that we are trying to mix involve earth sciences, history, and economics. And we are, 1, 2, 3, 4 co-authors that are only economists and have no formal training in either history or earth sciences. But I say this without any shame. I think what counts is the spirit. So let me just give a quick round of motivation, if you want. Climate migration is a potential social tipping point in our modern societies. We are already seeing strong migration flows from low-income countries. Basically, they have doubled in the last 30 years. So you get an idea, the current number in official statistics is about 2 million migrants from tropical countries outside of the countries to other nations. Okay, that's the current rates. It's about 2 million per year. And this flow is increasingly associated with climate degradation in nations that are heavily dependent on agriculture. This process is often confounded with weak institutions, violence, and strife, which is one of the reasons why it's not always associated with climate. But the good thing about the climate econometrics is that climate, for all practical purposes, is exogenous. Now, countries at the receiving end also have been affected. With an increasingly negative perception among the general population, migration has contributed to social and political polarization, which itself is associated with the recent deterioration of the geopolitical landscape. But the problem is that the scale of migration thus far will probably pale in comparison with what the future holds. Because, as we've seen, climate is going to further deteriorate. And as it does, the map of uninhabitable ecosystems will continue to expand. And in particular, it will expand in the regions that are already the most affected and that house some of the largest concentrations of people today. As I said, regions that will suffer the most are often those already degraded. You can see this at the IPCC latest assessment report. And this suggests that the trends that we've seen may soon become highly non-linear. And I'll talk about the non-linearity quite a bit in the presentation. Thus, mass migration, which if you think about it has been the main adaptation mechanism of our species to survive climate change in the past, may well constitute a key social tipping point in our modern, overpopulated societies. So what do we do in this paper? We try to advance the study of climate migration and it's the relation between climate and migration relative to previous studies. And let me point to the key challenge. The key challenge is data. I mean, it's not that the data that we have is not good. It's pretty good, actually. It's I'll show you. It's a panel of 30 years, 150 something countries. It's pretty good, but it's typical post-war data. And in the post-war, epoch, we have not seen any significant dislocations in climate yet. So here I'm going again to the non-linear part. The non-linear part is about to start now. We haven't seen it yet. So what's going to be our approach? Our approach is to, and this is how we also extend the literature a little bit, we're going to put our historian hats without any formal information in history, but still. And we're going to study the past, because the past indeed has many episodes in which we can identify precise and severe climatic events, and we know either from the archaeological records or from written records, usually both complement each other, we know the effects they have on the societies that suffer the shocks, but also, importantly, the societies that receive migration. And I'll show you that this, I think, gives quite a strong support to the notion that we have intuitively that, you know, a 3-degree world is going to be a lot worse than what the climate models are giving us. Because the climate episodes that I'm going to show you, well, I'll actually only show you one. I mean, this is much smaller than what we expect to happen in the Earth in the next 50 years. Okay? and I'll show you the consequences. They're pretty dire. That's one thing. So that's studying the past. Then we're going to extend the studies about the present with the standard data. We're going to revisit the empirical literature on climate migration, and we are going to extend previous studies in several dimensions. Most importantly, we are going to interact the impact of climate with income levels of different climatic zones. And this is going to give us an idea, and I'll show you that results actually do depend on income levels. And I think they speak very naturally with the presentations that we've seen, actually the last presentation that we saw, and the previous one by Tama, in the sense that the capacity of adaptation does seem to be playing a role. And then we're going to use this estimated reduced form empirical model to project future migration under different scenarios. We're going to use two IPCC scenarios, one where the temperature increases. So of course we're not going to use the 1.5. I think there's consensus that that's kind of gone already. So we're going to use the 2-point-something scenario, and then the more extreme SSP5 that has a temperature increase somewhere between 3.3 and 5.7, I believe. And although this is not yet in the paper, we are working hard on constructing a third scenario, which is a tipping point scenario, one in which the Atlantic meridional ocean circulation ceases. And the reason is that we haven't done this yet is that there's it's not clear what the implications on temperature are of this exercise. But I'll show you from the historical records also that this is a big deal and it's worth studying. Preview of the results. The past shows that the history of human migration is strongly related to climate change. We have 4 selected episodes in the paper. I'll only have time to discuss one, but they basically show that climate disruptions leads to significant outward migration, and furthermore, it has very highly disruptive consequences on societies at the receiving end. And they constitute one of the main elements, but I would say the main, precipitating violence, regime change, actually, in many cases, and in some cases, complete societal collapse. Actually, the one that I'm going to share with you, which is the end of the Bronze Age, is classified as the latter, complete social collapse, in the formal sense of what the concept of collapse means. Then, a preview of the results of the present, we confirm, I would say, a non-linear relation between temperature changes and migration. It's an inverted U shape, so a lot of points in common with papers that we've seen today. And very importantly, the non-linearity is stronger in poorer countries, probably reflecting less capacity of adaptation, or perhaps poor institution, or perhaps both. Indeed, despite having the experience as yet the smallest increase in temperatures relative to other zones, the tropical climate zones, which start from a higher temperature, are the ones that have exhibited the largest increase in outward migration. And this, again, I think speaks to us about the importance of the non-linearity of this whole process. Our results about the future, when we use our model to project these different scenarios, we actually find moderate effect on migration increases under, well, moderate climate scenarios. But under the more extreme climate scenarios, we find a doubling of current cumulative migration from tropical zones, which is a result that surprised us in the sense that we believe, or at least intuitively, it seems small. I'll show you. I mean, migration from the tropics has already doubled in the last 30 years. So projecting to 2100, and it has doubled with an increase in temperatures of 0.6 degrees. It's not even 1 degree in tropical zones. So projecting, an increase of another 4 degrees and just getting a doubling effect seems rather low. So some thoughts on this I'll share right away. I think there are two things that we're not capturing well in the nonlinearity, and this is the data restriction that I was telling about. One comes from the earth sciences. Ecosystems have this important property that the more shocks you throw at them, they start to lose their resilience. And at some point, that resilience is completely lost, and ecosystems enter a tipping point, and they don't recover. You can just take a stroll if you have a couple of days through the mountainous zone in Santiago. And I did. I live actually in the top of a hill. And this year was beautiful. All the trees recovered. And I did like a census, like an informal census. And I counted that roughly only 50% of the trees are still alive since the time I moved there, which was 7 years ago. So that, I think, is a very good example of, one drought in Chile of, 10 years or 6 years, 7 years, basically destroyed the half of the life of trees in that area. This is, I don't think, is well captured yet because again we are at the start of the nonlinear process. But this nonlinearity is typically not included or this characteristic of ecosystems is typically not included in models, and I think that's one of the reasons where we might be underestimating the nonlinearity. And another one that's more economic in nature is that we are going to be projecting migration with the projected incomes of these scenarios. But as climate, further deteriorates, of course, GDP in the most affected regions is going to fall, and that, by the same argument that I just described, is going to enhance this relationship, and we are not covering that in the simple sort of partial equilibrium exercise that we're doing. Let me just quick outline. I'll only have time to describe the end of the Bronze Age, which you cannot miss that one, trust me. And then I'll quickly go through the quantitative analysis, describing the data and the empirical approach we follow with the post-war data. I'll describe the main results, and then I'll show you the projections for the two IPCC scenarios. And I'll describe a little bit, if I have time, the motivation for this other perhaps more ambitious exercise, which is to simulate migration under a tipping point scenario. Great. Let me talk a little bit about the Bronze Age. The Bronze Age, just to give a little bit of context, marks the transformation of life of human settlements from dispersed Neolithic villages into what we understand as the state, and eventually small regional empires as well, which were characterized by high population concentration. And this started between 4,000, 3,000 before Christ, depends on exactly where you look. And it ended quite abruptly at the episode that I'm going to describe, which is around 1200 before Christ. This period witnessed technological improvements, irrigation systems, bronze tools, wheels, wagons, and also increasing social complexity. There's marked social differentiation and inequality. This is where inequality was created, essentially, in the Bronze Age. There's writing, and importantly, there's hierarchies for administrating these vast agricultural resources that the state starts to produce. Now, the late Bronze Age also saw a growing trade network between what came to be called the Club of the Great Powers. Okay, and this is like the top 5 universities in the US. There are like 15 of them, right? It depends on who you ask. So who's in the club of the great powers is not clear. Let me just give you the names that I'm sure about. Egypt, the Hittite Empire was one of the dominants. Mitanni was right south of Hatti. Kassite Babylon, and minor players included Assyria, which was a sort of a rising power and threat to Mitanni and Egypt. Arsawa, and many city-states of Mycenaean Greece. And here I want to put the accent, Mycenaean Greece, because this is where the migrants are going to come from in this episode. Okay? And geographically, this is important for the story, the region sits between two major climatic regimes. One is dominated by North Atlantic winter precipitations. This is towards the northwest of the region I'm going to show you in a second. And at the other extreme, we have the monsoon summer rain system towards the southeast of the region. And importantly, shifts in the range of Earth's wind circulation cells. You know, there's 3 circulation cells going up, 3 going down. It's the same cells, it's kind of symmetric. They basically describe the climatic regions of the world, and they shift. They could shift, they shift from winter to summer, but they can also shift in multi-year episodes and even several decades. And these shifts correlate with cycles of solar radiation intensity. So how strong the sun radiates, that is not constant, it has cycles. There are many cycles from 11 years to 2,400-year Hallstatt cycle, which is actually the most important one, and it will be important for the story that I'm going to tell you. So this is the map. This is how the Bronze Age looked right before, not right before, but close to the collapse. So you have at the right of the figure, you have Mycenaean. Does this work? I don't know. Well, I show it here. This is Greece, right? This is Proto-Greece, right? The Mycenaean Greece. Then you have the Hittite Empire. This is Mitanni. This is rising Assyria. This is Babylon, dominated by the Kassites. And this is Egypt. Notice that Egypt, at this point, was an empire. It extended beyond the Egypt that you know today. It also included most of the Levant. So what happened? Around 1200 BCE, during a Hallstatt radiation minimum, a multi-decade drought appears to have hit several states in the north and northeast of this region. And this is documented by Egyptian and also Hittite trade contracts. So the archaeological evidence for the Hittite Empire and Egypt is very rich when it comes to this, to compare it to other cultures, say. And they both documents basically the Hittite king imploring the Egyptian pharaoh to send more grain. And this is happening a couple of decades before the big invasion that I'm going to describe now. The drought seems to have hit Mycenaean Greece the hardest, triggering mass migration into Anatolia. So basically, it's like all this purple area here became depopulated. So first, they started fighting between each other, and there's looting, burning of cities, total abandonment of the main population centers, and all these people, and these are not only warriors, these are families basically migrating, and they migrated to the east. They migrated this is Arsawa, this is Hatti, this is one of the main empires. Consequence, they burned Hattusa, who was the capital. The Hittite Empire completely ceased to exist. There are no more written records after the invasion, or population displacement, as you want to call it. Then the Babylonian Empire also collapsed, and the territories held by Egypt in the Levant were also lost to this population displacement. So when it comes to understanding the effects of climate change on migration, I think this is a great example in telling us that migration is not like some little nuisance that you should add to the GDP or welfare effects. I mean, in this episode, it's the main thing. It is literally the main thing. Without migration, Hatti would probably have survived just by trading more with Egypt, which was not affected. I mean, it was affected in terms they were invaded, but they weren't affected climatically. So this is one good example of the effects that we've been kind of hinting at. What's the aftermath of this episode? we have a 400-year dark age. And the reason is back then writing was pretty hard. The writing was represented, like if I wanted to write this, well, there was no pointers back then, but if I wanted to write a shoe, there was a word for the shoe. So, you had to keep track of thousands of words, and the only people who did that were the scribes. So only the scribes knew how to write. But the scribes are only useful when you're writing contracts. And for that, you need a complex society that administrates resources. And the very concept of collapse is that when something bad happens, the level of social complexity that can be sustained basically drops a couple of notches. And here it dropped quite a few notches. So empires cease to exist, at least in this broader region. So, very high unemployment rates among scribes. So nobody to carry the torch, no more writing. So we have no idea what happened, or very little idea what happened in the next 400 years. Which actually is mentioned in one of the Plato's famous books. I don't remember which one, the Timaeus, I think. Anyway, let me make a summary of the historical episodes because I'll only show you one. These selected episodes illustrate a tight relationship between climate change and mass migration, particularly for the severe and long-lasting events. And it's usually accompanied by violence, strife, socioeconomic impacts that range from regime change to societal collapse. Now, you might say, look, I mean, that's interesting, but it happened a long time ago. Why should we care about this? And I kind of sympathize with that. I mean, our societies are very different today. But I'm going to give you 3 points for you to wonder and just think about it a little bit, okay? Climate disruptions in all the episodes that we describe in the paper were actually much milder compared to the scenarios that we're projecting. So that's one thing to keep in mind. Second, disruptions were local. This disruption that we're talking about is global in nature. It's called global warming for a good reason. And third, in all these episodes, this is maybe a one-year cyclone or a multi-decade drought, like the one I described. But that's not where we are heading. We are heading for a very, very long-lasting stress on our environment. So basically, 3 differences with the past that, in my opinion, tell us that, the past is a very imperfect mirror, but this is cause for concern, not reassurance. Let me move into the present. Let me just describe briefly the data. We use migration. For migration data, we use census data from the Department of Economic and Social Affairs and Population Division at the UN. And we construct immigration stocks in a 5-year frequency for 154 countries between 1990 and 2020. We also use data on agriculture and weather. We use the agriculture data, the crop and livestock production and utilization, and land and water section from the FAO's data collection. And this is to identify the maize growing season for each country in the sample, okay? So this is not the average temperature in a year in a country. It's the temperature at the time where the maize is growing in countries, okay? So that required more work because obviously it's not the same time for each country. But this is important because previous work has found that this distinction is key. I mean, if you just put the average temperature in 1 year, you don't get much effects on migration. But if you use the temperature anomaly, if you want, at the growing season, then the thing is completely different. In terms of economic temperature, we use the climate change knowledge portal from the World Bank that provide historical series at the country level. For economic data, we essentially use the World Bank for population and GDP. And we also classify different climatic zones. This is not very important for the regressions themselves, but it is for the classification that I'm going to show you when we summarize the results. And for that, we take a country. Countries, many times, especially for big countries, they have different ecosystem and sort of climatic regimes. And therefore, we're going to take the one that is dominant, and we're just going to classify the whole country into whether it's temperate, arid, cold, or tropical climate. And you can see Peel for more details on how this is done. This has a lot of information. On the one hand, is the graph, just the map of the world, dividing these regions that I spoke about. So Canada, Russia and China are cold. The United States and Chile are temperate. The equatorial Africa is basically. This is arid, I'm sorry, and then this is northern Africa. Equatorial Africa and the north of South America is essentially tropical. Okay, so here I just want to point out a couple of numbers that I have in the table down, which summarizes both the migration flows. That's in the first row of each of the different climate classifications. That's how the stock of migrants has changed through time. And then what you have in the row immediately to the right is how temperature has changed. So for example, let me just go right into the meat of the analysis. And this is actually highlighted with red. In tropical regions, migration flows went from somewhere in the 36 million stock at the beginning of 1990 into the 85 million. So that's more than a doubling of migration from tropical zones to other countries of the world. But the temperature increase was just from 24 to 24.6. Again, this is the temperature increase during the period in which maize is growing. Okay? That's actually the region with the smallest increase in temperature. And you saw the highest increase in migration. This is the empirical model that we estimate. So essentially, our dependent variable is the ratio between immigration, the stock of migration from the country, from a particular country in a particular year, with respect to 1990. So basically, essentially, this is the stock of people, I don't know, from Zimbabwe that are not living in Zimbabwe. Okay, that's for the case of Zimbabwe, obviously, for one particular year. Okay. T is the mean temperature of the maize growing season of that country over the previous 5 years. Y is the log of GDP. Population is the ratio between the population of country Y in year T with respect to its population in 1990. And then we have country and time fixed effects in the regression. And let me describe the regression a little bit, because this is kind of quite important in the results I'm going to show you. So we have a temperature entering linearly, quadratically, but also very important, and this is one of the extensions of over the paper that is closest related to ours, which is also the paper of the discussant. So there'll be some action there, I'm expecting. We interact temperature and the quadratic term of temperature with the level of GDP as well, and we'll see that this actually leads to some interesting implications. Let me show you. Yeah, you cannot see any. I mean, if I can barely see this, I'm guessing you don't see anything. So let me just summarize. We choose our baseline specification is the third column. That's basically because we find that essentially the driver here is temperature, not so much rain. So we discard the one that's more complicated. We just stay with the baseline, row 3. And here we have highly statistical coefficients associated with the increasing temperature, but they play out in a non-trivial way. So if you just take the linear effect of temperature, it gives you a negative relationship. So the higher the temperature, the lower the migration. But that's why it's important to take the non-linear form. So when you take the quadratic term, that has a highly statistical significant positive effect. And that means that at some point you reach like the optimal temperature. And after that, migration actually starts increasing with temperature, which is kind of, we've seen this graph in different forms throughout the whole conference, actually, in other elements, not in migration, but it's also true for migration, as I'm going to show you. And also we interact this with GDP, both the level of temperature and the quadratic term of temperature. And basically the conclusion here is that the richer the country is, the less convex the relationship is. Okay? let me say this in other words, the poorer the country is, the more non-linear this relationship is going to become. Okay, and this is going to be particularly important for tropical countries, which is where I'm going to concentrate the discussion. So these are the results look if we just take, say, the global averages for, say, GDP and population and so on, and we just do a thought experiment on what happens with this relationship as we vary temperature. This is just to give you a graphical representation of the regression that I just showed you. This is not a projection of anything yet. This is just the regression that I showed you. But when we when we differentiate this by the level of GDP of different climatic zones, we get a picture that looks like this, actually. And this is kind of more interesting. It shows that, first of all, different climatic zones are at different starting points. Here I'm going to use my finger. So basically, let's take the cold regions. They're here. Okay? So they're at the declining stage. So when weather warms up further, migration is going to further decline here, right? Because, people have, it's nicer to live there. And maybe expats that are living in Indonesia are going to return to the UK, for example. So that's that's kind of the effects that we're capturing here. But you take the tropical countries, they're already here, okay? I should say this is the emigration stock relative to 1990. So, for example, tropical countries, which are here, this blue point here, they're already at roughly double or a little bit more the levels that were at 1990. And importantly, they're already in the start of the nonlinear increasing zone of migration. So an additional increase, 1 degree in temperature, is going to have a higher effect on tropical zones because they have lower GDP, and that's what the regression tells us, than it does, for example, at richer temperature zones where the relationship is still nonlinear, but the nonlinearity is not as marked. Okay, that's kind of the conclusion here. And I'm just going to simulate these two scenarios, SSP2 with a radiative forcing of 4.5 and SSP5 which has a radiative forcing of 8.5. I think that's what this nomenclature stands for, unless I'm terribly mistaken. Great. So these are the results. Essentially, as the weather warms up, you get a decline in migration for the areas that I showed you that were still in the sort of the left-hand side of the figure, right? Because it gets nicer, according to this model. But the tropical zone, which is where the most migrants are coming now, this thing gets worse. It doesn't get terribly worse. It gets 25% worse in the model scenario. Okay. If we now go to the more extreme scenario, in which the temperature increases somewhere between 3.7 and 5 degrees, which is the range of this particular IPCC scenario, then we get roughly a doubling of the current migration from tropical countries to the rest of the world. Okay, so again, are the effects large? I mean, they're not. I mean, in terms of magnitude, this is 60 million people, an additional 60 million people migrating. But I would have expected larger effects, and probably this reflects the issues that I discussed at the beginning, that we are probably reporting a sort of a lower bound on the estimates, because this nonlinear relationship, there are good reasons to think that we are just beginning to capture its form, and as more extreme events occur and as temperature increases, we will really start seeing the true nonlinear relationship, and for the reasons that I described at the beginning, that will probably be a more nonlinear relationship, so stronger effects. I have 34 seconds to describe one scenario. I'm going to have to pass on this one, unfortunately. But let me show you this picture, okay? Tipping points. There is a tipping point that we kind of fear. It's called the cessation of the Atlantic Meridional Ocean circulation. This circulation, what it does is it basically redistributes temperature from the equator to the North Atlantic. So it makes the North Atlantic not as cold and the equator not as warm. Okay? That's how we live. That explains to a large extent the fact that there's the range of habitable zones in the world is large. So let me show you a little bit of prior history. This is where the Holocene starts. This is basically here, right here. And the start of the Holocene, it turns out, I think that's my own alarm, actually. It's kind of embarrassing. I'm interrupting myself in my talk. But anyway, so what happened here? So this is not the last glacial maximum, okay? The last glacial maximum is here. So the Earth started to warm up about 20,000 years ago in a very, chaotic way. So you get this spike, and then you get this, then it settles down around this temperature. And then you have this huge decrease in temperature that lasted for 1,000 years. And this is the temperature measured in North Atlantic. It comes from ice cores records and so on. And this is what is called the Younger Dryas episode that lasted 1,000 years. And this is essentially caused by a collapse of the Atlantic meridional ocean circulation. That's what happened. It was a natural accident. The Earth was warming up, and as it warmed up, it accumulated a big chunk of water in a huge lake, the Lake Agassiz in North America, and it turned out that the borders of the lake were also made of ice. So as that ice melted, this huge lake got dumped into the North Atlantic in a matter of months, and that essentially made the water less salty. And for this ocean circulation to occur, it has to be salty. We can get into the details of why, but that's essentially what happened. So basically, we don't have the scenario of what will happen now if this stops, but we do have the scenario of what happened before. And what happened before was that humans were actually starting to domesticate agriculture back here. There's archaeological evidence of this. And they had to stop, and that's an understatement. They basically, human population almost collapsed through this episode. They went back to hunter-gathering activities, and then when the circulation started flowing again, you get this huge spike that occurred over, 30, 50 years, and that's where the Holocene starts. So in a summary, is this a big deal? Well, if it marks the beginning of our current epoch, I would say it's kind of important, just intuitively, right? But we are left with the task of trying to actually quantify this scenario. Because this scenario, I should say, this is the last thing I'll say, is important because this implies that countries in the North Atlantic are essentially going to freeze. So they are also going to move, but they're going to move in the other direction that I just showed you. So now we're going to start having migration from rich countries and also from poor countries. So it's not clear where they're going to migrate to. Because essentially, the world becomes a much harder place to inhabit. To conclude, climate migration could represent a social tipping point if it leads to within-country conflict and polarization, and between-country conflict and further deterioration of international cooperation, which are both already happening. And it's a social tipping point because this cooperation is a prerequisite for international climate and environmental agreements to get traction. So climate and the effect on migration will probably get on the way of that very needed international cooperation. Past episodes suggest that climate-induced migration is not a nuisance that slightly amplifies GDP or welfare losses, but it's often the main thing that causes the disruption. Estimates with data since 1990 suggest migration from poor nations will further increase, although data scarcity in the nonlinear region probably leads to an underestimation of the effects. And just to end up, we highlight two immediate policy priorities for the analysis. One was touched upon by Tama in her talk. We should put high priority to identify and to finance the key investments that are needed in adaptation to mitigate emigration from poor countries. But of course, those are the countries that have the least resources to adapt. So we should think about that problem hard. And second, I mean, you can adapt and mitigate this to some extent, but just the magnitude of the migration that is coming, I don't think is something that can be stopped by a wall or, you know, a growing number of dictators around the world, because the alternative for people that are living in these regions is death. I mean, if you take all the money that you save and you take a boat to cross to Sicily with roughly a 10% chance that you and your children are going to die, that is telling us something very strong. I mean, these people are not going to be deterred by a wall. So basically what's the message here is that climate migration is inevitable, and we do not have, to my knowledge, any international agreements on this sort, and this is probably something that we should be also talking more about today. Thank you.